Hello, welcome back. In the previous segment we looked at the concepts of dynamic memory allocation, and as has been our pattern, we're going to in this segment solve some problems using the concepts that we learned in the previous segment. So it's important that you type along with these and look at what's going on in the debugger as we solve these problems that use dynamic memory allocation. Draw some pictures. I'm going to say that about 10 times. When you're making these dynamic data structures, it gets kind of abstract. You have a pointer that points to the memory that was dynamically allocated, and if you don't have a piece of paper on your desk with a picture of what's going on, then the code starts to become too abstract to really get your brain wrapped around, and you start coding things without really having a good understanding of what's going on. So type along, draw pictures as we're doing it, and hopefully this will seem fun to you and not overly complex and abstract. That's my objective in this explanation. So let's look at the spec which we'll use to exercise some dynamic memory allocation. We're going to jump right into allocating space for structs. So we're going to make a new data type called a customer, and this customer will have a name and an account number and an amount owing. I guess a customer would be much more interesting in real life. This is going to be a small example because I can't fit too much code on the screen while I'm recording it. So once we have the customer data type, then we're going to allocate space for an array of customers. First statically off the heap, and then we will fill in a couple of customers' data, and then we'll allocate some space for these customer objects dynamically off the heap, and we'll fill in a couple of those, and then we're going to allocate an array of 10 customers dynamically with memory allocation done separately for each customer. So we will revisit this slide as we go through it. I don't expect you to remember all of these. In fact, I don't expect me to remember all of these. Let's go out first and let's define a new data type that represents a customer. He'll have name, account number, and an amount owing. So I can use this one that I had from the last segment. So I'm going to define my new data type, and I'm going to call this data type customer, and it's my convention to use all uppercase when I've typed a struct. So we're going to declare space for the name of the customer. Let's allow space for 40 characters. And see, I already forgot. I know we want to declare the amount that they owe, and I think we had a customer ID. So we have in one of these things we have 40 bytes for the name, 4 bytes for the customer ID, and 8 bytes for the amount owing. So the size of this struct, this new data type, is 8 plus 4 plus 40. That should be 52. Okay, now that we have a new data type, we could do something very simple. Our first requirement was to make an array of customers that is allocated off of the stack. So that's the same as any array that we've used up until now, except each element in the array is a customer. So the spec said fill in a couple of these customer objects in this array, and I'm going to say that my customers sub0 dot name is Bob Smith, and there's a bug there. Do you see it? I'll go back and fix it in a minute. Dot customer ID dot amount owing. They owe us $123.45, and the customer ID for this one is 12345. Okay, so here's the bug. Inside of double quotes, the data type is a character array. You cannot assign an array to an array. You have to do it one element at a time. So I hope you remember that when you're moving around a string, you don't have to write the function to do that. You can call a function string copy, strcpy, and that function is in the train library. Okay, so the spec said fill in a few of them. I'm not sure that we would gain very much by making another one. Let's set a breakpoint here and make sure that things compile and run. We're doing what we should be doing. So my customers is an array, the 0th one. The data type of the array elements is customer. So the 0th customer, his name is Bob Smith. Here's his customer ID and his amount owing, and we have junk in there because we have not yet executed that statement. So if we execute that one statement, now the amount owing is what we entered, $123.45. Okay, so we have an array here of customer objects, and I'm going to flip back to the spec. Okay, so we allocated space for 10 customers, and we did it on the stack, and we filled in one customer's data. You can make up some more. And now we're going to allocate an array for 10 customers dynamically, and we'll fill in some customers' data. So let's go back and do that one. So this time, instead of subscript syntax, I'm going to use pointer offset syntax. So my dynamic customers is a pointer to a customer. So see what happened here. On the stack, we allocated, how many bytes of space did we say each one of those was? Times 10. So that was 40, 44, plus 8, 52 bytes of space times 10, 520 bytes of space on the stack. When we declare this pointer, how much comes off the stack? 4 bytes of space. So this pointer is a local variable, and it's on the stack, but what it's going to point to is not going to be on the stack. So let's take this variable, it's a customer pointer, and we will say let's calloc, maybe enough for 10 customers, and we will use size of customer. Okay, I want to, let's just compile and run that to make sure that I haven't done something wrong. Okay, this is interesting. When you look at my dynamic customers, you can't see quite as much as you could see with my customers. My customers is an array on the stack, and the compiler right here, including the debugger, knows that there are 10 of them, and we can open it and we can see all 10. My dynamic customers, when you open it, you can only get to see the first one. Now that's a problem because people think that there's only one there, but there isn't. There's plenty of space. There's exactly the right amount of space for 10 customers, and because it's on the heap and not the stack, it's not as easy to see in the debugger. We just see the first one, what the my dynamic customers points to, which is the 0th element of the array. Okay, so let's say my dynamic customers sub-0 name. In fact, I'm going to take this piece of code that's the same and then just change the name of the variable. Let's put another one in there. So let's fill in the second element to make it clear what we can and can't see in the debugger. So the first element is going to be Mary Jones, and making up numbers for this first object in the array of dynamically allocated objects. And while I'm here, near the bottom, I will free the my dynamic customers. And you know, in the slides I told you what you should do after you allocate the space, and then I didn't do it. So you should check and make sure that my dynamic customers, if it's equal to null, that means that the calloc failed. So there was not enough room on the heap for that. So we better tell the user what happens. And you can put something in here like call tech support immediately, and they won't know what to do either. And let's exit with some error code. -1 means that, okay, so we don't expect this to happen because my dynamic customers will have a valid address in it, and it will not have null in it, which is defined to be a 0. That's quite convenient. When you hover over it, it will show you that null is defined to be a 0, and calloc will return null when it fails. And when it doesn't fail, it will return a pointer to the block of memory that it allocated for you. So let's put a breakpoint down here and run to that breakpoint and see that we have stuff going on. So we're going to fill in the first element, my dynamic customer sub-0, with Bob Smith and 1, 2, 3, 4, 5 and all of this. Now when we start to fill in the second one, it's not as easy to see here in the debugger. For me, that's a big problem. I need to be able to see everything that's going on. I don't just believe that it will work because the previous one worked. So what I do is go into a watch window. So we're in debug and we have auto and locals, and in the watch window you can watch whatever you want. So I want to look at my dynamic customers, and there's the address in my dynamic customers. What I really wanted to look at was my dynamic customers sub 1, and you can see that my dynamic customer sub 1 has Mary Jones in it, and now as we execute this code, 54321 is the customer ID and 456 and so on is the amount owing. So dynamically allocated memory, you can't see it as easily because it's not really a local variable, it's on the heap. But that doesn't mean that you don't need to be able to see it. You need to be able to see everything, and you can make as many of these watch windows as you want, and you can watch whatever you want. You can put my array sub I here, and the debugger will show you what is the ith one. So this will change if you make a loop and loop through the elements in your dynamic array. Oh, well, this will be interesting to see what the debugger does with this data when we free the my dynamic customers array. I'm going to hit F10 now, and that is very nice that it actually goes and destroys all of the data that you don't have access to. The reason it's nice is because you won't accidentally go back and see correct data there and think that everything's okay, which it isn't. So all of the data that you allocated off the heap using this calloc was given back and destroyed by this debug environment, which is quite nice. Okay, so we haven't done everything we intended to do yet. Let's allow that to exit. Okay, we allocated an array of 10 customers dynamically, and we filled in a couple of customers' data. Now this one is different. Allocate 10 customers dynamically, with the memory allocation done separately for each customer. Okay, here's the issue. If you have a lot of memory that you want allocated, suppose instead of 10 customers we needed 10,000 customers, in an array or in a block of memory that you allocate dynamically, it has to come in one contiguous block out of RAM. There might not be room to get this huge block of memory contiguously, and the calloc would fail. So if that was too big, eventually the calloc would fail. So what we would like to be able to do is to declare, or let me say this carefully, we would like to be able to allocate the space for each customer one by one, so that we still have the space for the customers allocated off of the heap, but it doesn't have to be a big contiguous block of memory in the heap. It can be little pieces of memory that are available in all the corners, and the operating system can go out and get that space that's available. Okay, so this one is a little bit complicated. Let's have a look at it step by step. Don't freak out on me. We're going to say we're going to make a customer pointer by individual customers, and then we're going to allocate space for 10 customer pointers as opposed to 10 customers. So my individual customers, I'm allocating space for 10 customer pointers. So that is an array of customer pointers, and I need a variable I. So what I'm going to do now is make a for loop, and now 10 times I'm going to allocate space for a customer pointer, for a customer. My individual customers sub I gets malloc size of customer. Okay, so we allocated enough space for an array of 10 pointers to customers, and then 10 times we allocated enough space for one customer at a time. And I have a bug. Good. Okay, this is an array of customer pointers. So when we do the allocation to my individual customers, we make 10 elements where each one is big enough for a customer pointer. And then 10 times each of those customer pointers gets some space allocated for a particular customer. So my individual customers sub 0, and what is its data type? My individual customers is a pointer, so we'll use the right arrow and we'll say its name, and we're going to use a string copy, Judy X. I must have spelled that wrong. Yes, I did. So the amount owing, and make something up. Okay, so I've put some information into one of those individually allocated customers. And here's the tricky part of this one. When you make the pointers, when you make this original declaration, you're saying I want to have an array of customer pointers. This first dynamic memory allocation is for the pointers, 10 pointers. That's 10 times 4 is 40 bytes of space. And then go through each one of them and allocate the 52 bytes each and allow these pointers to refer to it. So this is the most difficult one, and it's also the most useful, because we can then allocate an array, a large array of objects, these things that we're calling customers, and we won't have used a large contiguous block of RAM. I wonder if we could look at that in the debugger while we're here. Oh, build errors, good. I'm going to have to correct something. My individual customers unknown size. Oh, it has to be done like this, I'm pretty sure. Okay, the only way that you can use the square brackets and have them empty is when you have an initializer that specifies how many there are. So this thing is a pointer pointer. So think of it the way I typed it, a pointer to an array of customers where each element in the array is a pointer to a customer. So we have a pointer pointer here. Let's see if we can look at this in the debugger and it will make sense for us. So in locals, my individual customers is at this address. I want to do this in the watch window. So here's my individual customers. It's this address, 64E98, and it points to an array of customer pointers. My individual customer sub 0 is Judy X, and its data type should be a customer pointer. So at that address we're seeing Judy X, and we're filling in the customer ID and so on here. So use the watch windows, use the debugger, make sure that you can see everything that you're doing, and working with these dynamically allocated arrays of structs, it does take some practice, but it's a very valuable skill for you to have. Let's go and see if there's another spec. Okay, we're going to write a function that will dynamically allocate space for one customer and return a pointer to that customer. Let's take that one first. So I'm taking that spec and I'm going to just paste it here in a comment. So what we're going to make is, it can be called a factory function. We're going to create something and give back a pointer to it. So we're going to return a customer pointer, and we're going to call it make a customer. So the function make a customer will declare a local variable, customer pointer, result, and then we will return the result, and in here we will create the customer, on the heap, and we will give back the address that was given to us. So we have a function called makeACustomer that gets some space off the heap and gives it back. This is not too interesting yet, but what we might be able to do is call that function here. So every time we want one customer, we could call the makeACustomer function, and it will get space off of the heap and give it back. Let's run that to see if I have any more typos, and there aren't. Okay, so this is an interesting function. I want to write a function here that's wrong. Suppose we want a function that returns a customer. makeACustomer, how about wrong? In case you're typing this, I don't want you to type code that's wrong, but I do want to demonstrate this. Well, let's make customer C, and let's say return the address of C. Well, the address of C is a customer pointer, and we did allocate space for a customer using this declaration. So let's see if that will compile, and it does. So what's wrong with it? The memory for this customer was allocated on the stack. When this function is over and the stack is popped, the space that we have allocated was automatically given back. So we returned a pointer to a piece of memory that we no longer own. That's different from this one, where we dynamically allocated the memory off the heap, and we returned a pointer to the block of memory that we do own. And the memory allocated on the heap does not go away when the function is over, but this memory does go away when the function is over. So that's automatic and off the stack, and this one is the correct way of doing it. So we manufacture a customer and give back a pointer to it, and we will still own that memory when it gets back. Okay, let's go back to the spec. Write a function that takes a pointer to a customer and ask the user to enter the data for that customer. Okay, we're going to write a function that takes a pointer to a customer and ask the user, so I'm going to call it getCustomerInfo. It will take a customer pointer, so we're supposed to say enter the customer name. That's the prompt. Now we're going to scanf into customer. Oh, we need a %s here, and we'll see if this works. I'm going to scanf using %s, and we're going to say go to customer's name, enter the ID. The amount owing is a double. Okay, that's worth trying. I don't know if it's right or not exactly. We're going to pass a customer pointer, ask the user to enter some data. We didn't check the data that they entered, we just put it into the object, and let's see if that's going to work. I've got so many examples in here, and I hope it's not getting frustrating for you. Let's make a customer, just one of them, first customer, and we're going to call getCustomerInfo, and we're going to pass in the address of first customer. I'm going to put a breakpoint there so we can watch this function and see if it does what we hope it does. So we're passing in the address of this customer, which we allocated off of the stack, but it doesn't matter. Any pointer to any customer would be fine. Now we're going in and we're going to print out, enter the customer name, and I'm going to say colon, so the customer has a name, enter the customer ID. Well, a colon would have been nicer. 123789, and that went into the customer ID field, and then enter the amount owing. I don't owe very much, $5.55, and there you see the approximation. So we're using floating point numbers, and they are an approximation. I typed $5.55, and that's what we got. Now we're going back. When we're going back to the caller, and because this was a pass by value, first customer should still have in it the information that we passed, that was returned from the getCustomerInfo function. So this is an example of writing a function where you pass an object by reference and get some information from the user. to fill up that object, and that object could have been dynamically allocated. It could have been one of the ones that was allocated here. Okay, let's go back to the spec. Write a main function that dynamically allocates space for 100 customer pointers. Keep track of the effective size of the array. Use the above function to add some customers to the array. Okay, dynamically allocate space for 100 customer pointers. And then we will start making the customers as we need them. It's getting a little messy again. I might throw all of this away. Here is my new spec. Okay, I need space for 100 customer pointers and keep track of the effective size of the array. Okay, let's make a customer pointer array. And you can put the asterisk wherever you like. In fact, that doesn't feel comfortable to me. I have a customer pointer. So an array of customer pointers. My customers gets, we need space for 100 customer pointers. Okay, and then we're going to allocate the space for some of them, keeping track of the effective size of the array. Use the function that we already wrote to add some customers to the array. Okay, so we have a function here that can allocate the space for a customer and return it. So let's say we want to maintain the effective size of the array. So our array has 100 pointers in it, but if we don't have 100 customers, there isn't any reason to go ahead and make 100 customer objects. So we're going to make these customer objects as we need them. So now let's say the effective size of the array when we start is going to be 0. That seems to make sense. And now when we create the first customer, we'll say my customers sub 0 gets make a customer. So that goes out and allocates the space off the heap for one customer, and now the effective size of the array is one more. Okay, is that making sense to you? When we're first starting, when the effective size of the array is 0, we want to make the 0th element in the array, and that dynamically allocates the space and then increment the pointer. Now we could take that 2 lines and just duplicate it, and we've made the second one, and we've made the third one. And whenever you are seeing duplicate code, it's wrong. I just wanted you to kind of have a feel for this. We could make these customers one by one and increase the effective size of the array, but it probably makes sense to have a function that does that. So we've got 3. We've got my customers sub 0, sub 1, and sub 2, and the effective size of the array is 1, 2, 3. So we've got 3 elements indexed 0, 1, and 2, and I can now call getCustomerInfo with each of those. GetCustomerInfo, and I want to pass in a pointer to a customer. So we allocate the space for the 0th one, and then we go and get the data for the 0th one from the user, allocate the space for the first one, go and get the information, and then the next one. I hope that's making sense to you. The pointer-pointer construct is really fairly difficult. When you have an array of customer pointers, the data type is a customer pointer. So it's the address of the first address in the array. And then we can start allocating for each of those pointers the space that we need for an object on the heap. Well, I'd like you to type this and get it running in the debugger. I seem to have this still running. So let's make sure that I haven't typed any mistakes before we leave this. Oh, and there's a build error. Warning, 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 error. My dynamic customers. Oh, perhaps that I have... Yes, that was left over from the previous example. And I see that I didn't free my RAM after I allocated it dynamically. That's bad practice. So where did we go? We immediately went to get customer name, customer ID, the amount owing, and then the next one, the customer name, the customer ID, and the amount owing. One more. Name, name, name. I thought we had done only 3. Oh, that one was left over. Yeah, I did 4. That call should not be there, because I did not allocate the space for that one. I wonder if any of you noticed that while I was typing it. So I'm going to get out of this, and now I'm comfortable that this is correct. Okay, just a short summary here now for dynamically allocating memory off of the heap for one object at a time or for an entire array of objects. And I probably should be calling these objects structs, because this is not object-oriented programming. That's quite different and only available in C++ and Java and other object-oriented languages, but C is not object-oriented. I'm calling these things that we're making, these structs that we're making, objects because it's just easier, although the terminology is not exactly correct. Choosing how to do the memory management, whether you declare the array all in one big block on the heap or you start to allocate them one by one, it depends on the nature of the application. How many of these things are you going to have? Do some of them have to go away, or can they all be created and all go away at the same time? You have to think about how you're going to manage the RAM that your program has available. Some applications, for example, need to grow and shrink their memory usage continually. So if it's a very heavy application, you want to try to make sure that you give back memory, the RAM memory, as fast as you can so that you don't have to use it all up. And if you have a good piece of code for giving back the RAM, you can write pretty good applications and have a very small memory footprint. And I think that what's difficult for us in this recording is to draw pictures of the data. So I've tried doing that in the PowerPoints a little bit, but a pointer, an array of pointers, you really have to draw a picture of it. So if you could see my desk right now, I have a picture of the array I was working with, the pointer, which is an array of pointers, and that's the only way I can work with it. I don't expect you to start right from the beginning working with pointers and not have a picture to look at and make it somewhat less abstract. Okay, well, this is a fairly difficult one, but I'm hoping that you're getting most of it and you're seeing that these things are not too scary. They're complicated, but they're manageable. I'll see you in the next segment.